Hello. I wanted to discuss some more engineering disciplines that connect with industrial design, namely thermodynamics, fluid dynamics, and heat transfer. Thermodynamics is a discipline that explains how energy is moved and the different forms of energy, and it provides a good context for other engineering disciplines. Fluid dynamics is the study of fluids in motion. So if you're designing something that moves through the air, like a car or a bike, or something that's a design in which you're moving something like medical devices where you're pumping blood, or or anything where you're moving a liquid or a gas, that's under the realm of fluid dynamics. And heat transfer is important when you're looking at particularly electronic devices where a great deal of heat is generated internally, and getting rid of the heat is one of the big challenges. Of course, heat transfer applies to many other areas of interest for industrial designers. So let's look at thermodynamics first. Thermodynamics is a study of energy, and typically you start with talking about a few laws of thermodynamics and the ideal gas law. So for gases, for example, you have a relationship between pressure, volume, and temperature. Pressure times volume equals nRT, the number of moles or number of molecules times a universal gas constant times the temperature. So if you look at proportionality and not get too involved with the specific numbers, you can see that pressure times volume is equal to temperature in an ideal gas. An ideal gas is a low pressure gas where the molecules don't interact and they don't take up any volume. And that covers most gases except for those that are operating at very high pressures or high velocities. So as you approach Mach 1, the ideal gas law doesn't work. You have a compressibility phenomenon that can be accounted for. But if you look at the basic equation, PV equals T, it explains a lot of things. For example, your car tire, if you think of your car tire as being a constant volume, which it basically is, the rubber doesn't expand very much. As you drive, it gets hotter due to frictional heating. So the T goes up, which means either the pressure or the volume have to go up, and because the volume can't go up very much at all, the pressure goes up. So that's why a hot tire has a higher pressure than a cold tire. And if you take a bicycle pump, which has a certain volume, and you change the volume without changing the temperature, the pressure goes up. So if I squeeze down on a bike pump, the pressure goes up. And these all make sense. And those relationships, again, are immutable except for when you deal with compressibility and at high Machs, which we don't need to look at. So if you're designing fan blades or jet fighters or something like that, you certainly have to worry about compressibility, and the ideal gas law doesn't work. Nor does the ideal gas law does not work for explosions and things like that, but we don't have to go further with that. Although it's interesting to look at that, but we'll stop with that discussion of the ideal gas law. The three laws of thermodynamics that are helpful is, there's actually a zeroth law, which I won't talk about here, but the first law is that energy is conserved, the energy equation. So there's a relationship between internal energy in the form of temperature, chemical energy, kinetic energy, which is velocity, and potential energy, which is pressure, typically. So there's a relationship between those forms of energy that doesn't change. So I can, if I push something fast, for example, I can change its pressure. If I add heat, I can change its temperature. And this is a bit much to look at without using some equations. But a good example, a simplified approach to the energy equation is the Bernoulli equation, which you're familiar with airfoil. So if you have a high velocity air over a section, over a form, and a low velocity under the form, the high velocity drives the pressure down, which produces lift. So you have a high velocity over the wing section, a low velocity under the wing section, so you have basically a vacuum cleaner that's pulling up the wing. So the velocity, the pressure is being turned to velocity. And you see this with a lot of things. You can take a piece of paper and blow over the top of it and the paper will lift up. And there's a lot of demonstrations of this. You see it in the Venturi effect in old carburetors. So I can, if I take air and suddenly accelerate the air, in other words, I increase its velocity, which is increasing its kinetic energy, I decrease its potential energy. In other words, I decrease its pressure. And this high velocity air then will act like a vacuum cleaner, and it will draw in fluids. And it was used for many years in carburetors, and still is in some cases. Ships traveling parallel to each other can accelerate the velocity, and the ships can be drawn into each other. And there's all sorts of interesting things that occur that can be described by the energy equation. So energy is conserved outside of nuclear issues. So that's important. And then the second law of thermodynamics is that entropy or randomness always increases. It's a famous law that comes into play sometimes in theological discussions and such. I can take a watch, throw it against a wall, it will break into a bunch of pieces. It becomes more random. If I grab those pieces and throw those against the wall, it's not likely to turn into a watch. It will become more random. And you can actually quantify this entropy and determine what reactions will occur. Reactions that have either the same entropy or an increase in entropy will occur. So liquids tend to turn into gases and these sort of things. The third law of thermodynamics is there's a baseline point where there's zero energy. So it just is sort of a bookkeeping issue. So when you get to absolute zero, about minus 273 centigrade or 460 Fahrenheit, there is no internal energy. The molecules cease to vibrate. And if it's in crystalline form, then it's truly at a zero energy state. And that's the third law of thermodynamics. And phase change is really interesting to talk about also. So in the realm of thermodynamics, it's a convenient model. Some of the language is a convenient way to express some chemical issues regarding phase changes. And for example, solids have tightly connected intermolecular forces of various sorts, hydrogen bonding, van der Waals forces. All these things are holding molecules tightly together. If you allow the molecules to vibrate, they'll break apart. There's enough vibrational energy to break apart these kind of weak molecular bonds, and then you get a liquid and then a gas. And that's a very interesting study. But moving on from thermodynamics to fluid mechanics, and fluid mechanics is divided into fluid statics, fluid at rest, and fluid dynamics, which is fluid in motion. So fluid statics I won't talk about much here, but it's pretty straightforward. Pressure is equal throughout a fluid, and it's an important concept when you're looking at pneumatic systems and hydraulic systems, and they're really important for systems design. And fluid dynamics is fluid in motion. So if we stop for a moment and say, what is a fluid? That's helpful. Fluids are liquids and gases, and unlike solids, which we talked about before, they have a finite viscosity. They will flow in time and with pressure or stress. They'll flow. They'll move. The molecules will move across each other and flow. So what's the difference between liquids and gases? Well, it has to do with that intermolecular issue I'd spoken of previously, how strongly attached the molecules are to one another. And that has to do with the pressure on them, it's squeezing them together, these intermolecular forces, the internal energy. That's what determines whether something's a liquid or a gas. So I can turn a liquid into a gas by changing the temperature or by changing the pressure. And I can also take some molecules, like hydrogen is a good example. It's a spherical shape, and it does not want to stick to another hydrogen molecule because it's round, and it doesn't have any polarity. So it's hard to freeze hydrogen. You can see that in the very low freezing temperature, which is basically absolute zero. But with regards to fluid dynamics, again, we're looking at the definition of fluids. You have compressible fluids and incompressible fluids, and just to introduce you to those terms, a compressible fluid is a fluid that you can compress. So these are gases, but they're actually low Mach gases. We talked about Mach velocity before. Basically low velocity gases. At high velocities, when you think of shock waves, when you think of Mach 1, the gases are now compressible, and they act like a liquid. So, or incompressible rather. And incompressible fluids then are liquids and high Mach gases, so you can't squeeze them any tighter. They don't move around. And that's kind of the simple explanation, but that's a good working point. So generally industrial design, you're looking at low Mach gases, which are compressible, and liquids, which are incompressible. So just some terminology. Then it's good to look at drag, which is often the issue you're thinking about. If you're designing a car, for example, you're concerned about drag. If you're looking at pumping or moving liquids like water or fuel or blood or something like that. That's a slightly different issue, which we'll get to in a moment, but all this discussion applies the same way. First, let's look at drag. There's three types of drag. There's friction drag, which is a drag resulting from these molecular connections between the liquid and the solid that it's running over. So as the liquid is running over a solid, there's a certain drag there. And the smoother the surface and the lower the velocity, the less the drag. And that, of course, applies to gases as well. So a smoother surface and a lower velocity will produce less friction drag. That's one type of drag. The second type of drag is pressure drag. And that's related to the difference in pressure at the front of an object and the back of an object. And again, a lot of this is best illustrated by demonstration. But in pressure drag, you have pressure drag increases with the bluntness of the form. So if I have something that's really square, let's say the water hits the front of the square shape and it has a high pressure, like it impacts it. And then behind the square shape, you have very low pressure, you have eddies. So the pressure drag of the square shape will be very high. Whereas a streamlined shape, you don't get the impact at the front, nor do you get the eddies at the back. So that has a lower pressure drag. And you can look at drag coefficients. They're related to the form of the object. So that's really important for industrial design. Again, biomimicry comes into play. If you mimic a fish, you're going to have low hydrodynamic drag or low pressure drag. If you try to take a brick and drag that through the water, you'll have high pressure drag, even if the friction drag is the same. And of course, this happens with airplanes and all such things as well. And this in transportation design is an issue because you want to reduce, especially the drag behind a vehicle. The low pressure drag is acting sort of like that vacuum cleaner and pulling back the car or the bike or the motorcycle or whatever the design is. And you want to allow the air to rejoin behind the vehicle, let's say, to reduce that pressure drag. The third drag is wave-making drag, which is only an issue with open channel flow. So if you put your hand in a stream, you'll see the water climbs up your hand a little bit, and that lifting of the water is wave-making drag. And that's a form of drag. If you have enclosed pipes, you don't have that kind of drag, but you do get the other types of drag. So in fluid dynamics, you have these three types of drag. Typically in industrial design, you're not so much worried about wave-making drag. You're worried about friction drag and pressure drag. Both of those, all three of these drags, are related to velocity. And therefore, going slow reduces drag. That makes sense. The pressure drag is very much a function of the form, so that's something you can work with as a designer. The friction drag is driven by the roughness of the surface. However, as it turns out, that leads to another issue with fluid dynamics, and that is laminar versus turbulent flow. Laminar flow is smooth flow where all the molecules follow easily predictable contours, velocity contours. Turbulent flow is chaotic flow, where the molecules move around rather randomly. And this is driven by the velocity of the flow and the viscosity of the flow. So if you take velocity and divide it by viscosity, which is a resistance to flow, you get a measure called the Reynolds number. And there's some other numbers you throw, or parameters you throw in there, but basically it's inertia, which is mass times velocity, basically, divided by viscosity. So if something goes fast, it has a high Reynolds number. If something has a really low viscosity, it has a high Reynolds number. And if the Reynolds number is around 2,000 to 2,300, it's a dimensionless unit, you get turbulent flow. So if I pour oil and water at the same speed, the water will become turbulent before the oil because of the viscosity. Gases tend to be turbulent all the time because they have very low viscosity. And viscosity is a propensity for molecules to stick. So that's that definition. So if often I'm in the turbulent regime. I have turbulent flow very often in a lot of things. Certainly with gases, very often with liquids. So in turbulent flow, you you get a different type of friction. What happens, well, not a different type of friction, but the friction drag is actually much less important with turbulent boundary layer than it is with laminar, or turbulent flow than it is with laminar flow. And the drag is often driven by the shape or the form of an object. And you heard me refer to boundary layer, and boundary layer is an important phenomenon here too. There's a small film of air or water, whatever the fluid is, that operates at a different velocity than the rest of the fluid. So if you think of the pipe, there's an area where the fluid is flowing through the pipe, near the pipe inside diameter, where it goes to almost zero. And those slow molecules drag the other molecules. This viscous drag is in play. And this occurs until you get what's called fully developed flow, where the boundary layer is no longer an issue. So this becomes an important thing for heat transfer as well. There's a area then of low flow fluid, whether it's liquid or gas, near a surface. And as you can imagine with heat transfer, because it's low velocity, it's not going to transfer heat so well, but we'll get to that in a minute. But this boundary layer then, if it's thick, tends to separate more easily than a thin boundary layer. So a thick boundary layer is a laminar boundary layer, and it doesn't like to cling onto the object very well. Whereas a turbulent boundary layer is a thin boundary layer, and it sticks better, and this is why you dimple golf balls. It's the classic demonstration of what turbulent boundary layer produces. Or you roughen up the surface of the leading edge of something, and you trip a turbulent boundary layer. This turbulent boundary layer sticks better. And you think of turbulence in a pejorative way, but a turbulent boundary layer has better adhesion. It's a lesser mass of air or water, and it sticks better. So it's a good thing, generally, to have a turbulent boundary layer. It will reduce the pressure drag. And with, well, I mentioned viscosity, we could talk about rheology, which is the relationship between stress and shear rate. And I won't go too far into that here. That generally we deal with Newtonian fluids like water, gasoline, air, these kind of things, where the faster they flow, the more resistance there is to the flow. There's a linear relationship. But you have other things like toothpaste and blood, which are Bingham plastics, which won't flow at all. If you turn a toothpaste tube upside down, it won't flow. But once you squeeze it, it starts flowing, and the relationship between the velocity and the pressure you put on to squeeze a tube is linear. And blood is the same. Blood, when it slows down, will tend to stop flowing. So in arteries, you have high velocity flow, and you get good linear relationships there. In the veins, you don't get that. You have lower velocity, and you get the stopping starting phenomenon associated with Bingham plastics. And it's also helpful for clotting. And of course, blood has deformable cells, and the deformability of the cells are important for capillary action and for clotting and these kind of things. So typically when you have what are called non-Newtonian fluids, like toothpaste and blood, they often have solid particles and liquids, or slurries of sorts. Then you have the other realm with food. You see a lot where you get pseudoplastic and dilatant flow, which I won't talk about too much here, but you can get different relationships between stress and strain. So you can get some things that when you pump them quickly, they lock right up like quicksand. Like oobleck is a good example, cornstarch and water. It doesn't like to flow quickly, but it will flow slowly. And then you get the other side where you get thinning at high shear rates, like whipped cream and that sort of thing. So you can mix things really well, but when you stop mixing them, they become viscous. And